particularly meant to be an equilateral triangle. Let's call this A, B, and C. And I'm going to put a starting point just randomly on the paper. And all we're going to do is roll this lovely dice, who cares, to decide which point to go towards. And we're going to, whatever point we choose, we're going to go halfway. So let's call A 1 or 2. If we get a 1 or a 2, we'll go halfway towards A. And this is going to be 3 or 4. And C can be 5 or 6. So I just rolled a 2, so I need to go halfway to the point that has been chosen at random, which is A in this case. So we could measure this. For the sake of speed, I'm just going to go roughly halfway. I think you can believe that. If we're on a line there, we're going to go put a dot there. And we're going to keep doing this for a while. We're iterating, so we're repeating. We get the last result and work from that. But the start point could be anywhere. I could have put the start point outside the triangle, and I could still head towards one of these dots. Let's just see what happens when I keep rolling the dice. I've just rolled a 2 again, so that was the dot I had before, and I've gone halfway from the previous dot, and that's my halfway point. So if I roll this one again, 1. I wish I'd rigged this now. From this dot, the last dot I had, halfway towards the 1, so we're just aiming towards 1. This is unlikely to keep going, but I don't know, place your bets now. 4. 4 is the B dot, so I've got to kind of from the previous dot, halfway on this line is about there, and I've jumped a long way this time. 1. Back towards A, so we're going in there. And I'm going to just keep doing this, so you've got the idea, I think, now. From the previous dot, we go towards one of these. 2. Your dice is rigged, Brady. 6. Excellent, we've gone all the way. This was the dot, kind of halfway is there. 6. 1. Back up here. 2. 5. All the way down here. I'm going to do this a lot now, Brady. But maybe this would be worth speeding up. I'm bored. But it's not that exciting, but interesting things are happening. We've created kind of some lines, but basically I've just made a bunch of dots on the paper. It's possible that something interesting would happen if I could do this quick enough that I wouldn't get so bored that I have to stop. But maybe we want a computer to do this. We have a problem with a computer though and random numbers. Like, generating random numbers is difficult when a computer has to do what it's told. But let's park that issue for another video, perhaps. If I could get a computer to roll the dice for me and put the dot on, then we could see what happens quickly. Let's do that. The screen has, just as we've got 3 dots. They're not even in a nice equilateral triangle. They can be anywhere. This thing says trace point. It's just going to trace where that goes. And the computer is, with its magic, going to choose A, B, or C and move that point halfway accurately this time. So you can see that it's leaving a mark anywhere it goes. So it's gone to A several times in rows, jumped to B, and then back to A, and then to C. But, I mean, doing a running commentary on this for any longer than I have done is probably not going to make anyone's day. So let's speed it up, go a little bit faster, and you begin to see something similar to the structure I had. The outlines get defined quite well, but I'm just going to speed up a little bit more because the outcome of this, I genuinely think, is slightly surprising, but also a little tiny bit frightening, because you start to wait, is that structure I'm seeing, am I imagining that? How is it dodging those little weird patches in the middle? Why is it never going in those? They're definitely triangles now. And then I start to see a shape which actually, if you've done any sort of investigating bits of recreational maths, this is a familiar shape. It's full of triangles. It looks like that trace point, wherever it's going, which is definitely going randomly. I haven't rigged this. This is doing it differently every time I run it. But it's dodging those triangles and it's making a shape which I think everyone can see now. This is called the Sierpinski gasket. It turns up all over the place. It's a fractal thing. You can see now, I think we've got enough to see that the big triangle has a black triangle in the middle and 3 copies of itself around the outside of that black bit. But then each copy of itself has a black bit in the middle and 3 copies around itself. And that's what a fractal is, this self-similar thing. You zoom in and you see a little copy of itself. But the fact this is genuinely coming from rolling a dice on a computer and doing it quickly makes me, I don't know, just slightly disturbed about reality.
I would have thought every point had a chance of being filled at some stage, but there are lots of areas that will just never get touched.
Right, so, and you can rig it. So I said you could start anywhere, right? So I could start with my point right in the middle. And then we definitely have a point right in the middle in that black. But what happens if you iterate it enough, it veers away from that. So the long-term behavior is what's interesting, is that even if you start in a black thing, the random going halfway moves you away from that black area. And you actually, the technical term for this shape is called an attractor. Some people, you may have heard of these things called strange attractors in chaos theory. It's kind of advanced maths in the end, but this shape is the attraction. And it's also just pretty. The fact that random behavior produces something which is very structured is a nice outcome. Well, we had 3 points. I mean, we could have 4, we could have 5, we could pick a number. Well, probably a whole number, otherwise counting the points is difficult. We could have 4 points and say, well, let's roll a dice, or a 4-sided dice, a d4, to go to one of those. What pattern would you get? You could say, instead of going halfway, go a third of the way, or 3/4 of the way. What will happen? Do any of them make patterns? Do they go chaotic? People have spent a long time fiddling with the rules. It's nice to find out for yourself, but there's one rule I'll show you which does something which nobody really expected. So I'm not going to go into details. This is worth looking up, but I've got a red shape and a blue shape, and they're kind of just summarizing 2 possible outcomes of the rule. Like, we'll start with a point, and with some probability we'll go to one of the corners of the red triangle. But with a small probability we'll flip over to the blue triangle. And every time you kind of roll a dice to see where to go, you follow this slightly more complicated set of rules, but they're just random. Like, you go here with a certain probability, and then you flip back to the red one with a certain probability. And if you look up this particular rule, you get this picture. After a while, you start to see these green dots appearing in what looks like a very structured way. In fact, it becomes very obvious if you run it long enough that the picture you're getting looks like something real. It looks like a fern.
Crazy.
This is called Barnsley's fern. Compare it with a real fern. It's surprisingly accurate. This is a nice example of how you don't have to draw something natural by hand. All the information for this fern is captured in a few lines of probability, like the rules of the game are the fern, or are a picture of a fern. It's actually really useful if you want to program video game graphics. You don't want to draw every tree, every fern. So if you can just kind of store all the trees and ferns as a rule and say whenever you want a fern, you just do that for a while. That is a much easier way to sort of... And lots of natural things turn out to have this fractal structure, that self-similar things, which means you can generate them by iterating stuff. Genuinely good graphics are coming from the fractal generated graphics rather than hand painted. To get the structure of a tree on repeat, if you just had one tree and you copied it, it becomes really obvious when you're running around the forest, like it's just a computer forest. But if it has this natural sort of variation with some randomness in it, you get much more realistic looking